Okay, Calc, we're on to section 2.2. We're going to talk a little bit more about qualities that polynomial functions have. So first of all, the graphs of polynomial functions, they will always be continuous and always be smooth and rounded. So like this first graph is the graph of a polynomial function. It's probably like y equals x to the third power. This middle one here is not a polynomial function. He is a piecewise function. He has multiple pieces because he has that break in the middle. This is a polynomial function. He's probably like y equals x to the fifth power because he's going opposite directions and has a bunch of highs and low places in there. And then this one is not a polynomial function because this is the graph of y equals the absolute value of x. So polynomials are the first one and the third one. The second one and the fourth one do not pass as polynomial functions. So we're only going to be talking about graphs like these today, okay? So even functions are functions that have that resemble x squared or x to the fourth power, any even power of x. This is considered to be an even function. This is the graph of y equals, let's see, the graph of y equals x squared is the faint line in here. The graph of y equals x to the fourth power is kind of the flatter tire. I told you guys the other day that I kind of lied to you when I said that x to the fourth power looks like a w. It does look like a w if you have like x to the fourth plus 2x squared plus 7 or something like that. But just y equals x to the fourth power without any of this extra stuff in there looks like a flat tire, okay? Now, it's the same way also over here when you have y equals x to the third power versus x to the fifth power. The x to the third power is this faint line here. X to the fifth power is a little bit flatter in the middle, okay? X to the fifth power will have extra bubbles in him like this one does when he has like x to the fifth power plus 4x cubed plus 7x squared minus whatever, you know. If he has more than that, he will be have extra bubbles in there, okay? Even and odd functions, one more thing that I will add to this, it's an even function if it's symmetric about the y-axis. I can't scroll anymore. Axis. And it is an odd function if it's symmetric about the origin. Okay. So, and not every x to the second power function is symmetric with respect to the x-axis. It's not all even functions. Like number 2 down here, for example. This is an x to the fourth power function, but because there's a 1 in there that's shifting him from here to the left 1 unit, he is no longer symmetric with respect to the y-axis here. So he is not an even function any longer. So this one says sketch the graph. I went ahead and gave you the graphs. This is what the graph of x to the fourth power but shifted to the left 1 unit. Left 1 unit. That's what he looks like. This is a graph of x to the fifth power, but the negative is going to reflect him. I'll put reflect over the x-axis. Okay, so it kind of flips him. This one's even, you can't really even see that faint line, but that's what x to the fifth power looks like. So he's reflected over the x-axis. He is kind of flipped down. That's what he looks like, okay? They talk about the leading coefficient test in your textbook. And what that means is it describes the end behavior of a graph. Oh my goodness, kiddo. And behavior. Hold on, guys. What's the matter? What's the matter? Okay, talks about the end behavior graph, and the end behavior is described like this. So we always say as x goes to infinity, y is doing something, and as x goes to negative infinity, y is doing something, okay? Or something, not, okay, blank. So, as x goes toward infinity, this is kind of saying as though x goes to the right, x is going toward infinity is as the function is going to the right. X goes toward negative infinity as the function goes to the left. Okay, so this guy right here, as he's going to the right, he's going up. So we would fill this blank in with positive infinity if we were doing this graph. As he's going to the left, he's going down. So this side would have negative infinity, and this is the end behavior for this graph. Okay. Now, if we were doing this graph, this second one here, it would be the opposite. As he's going toward the right, he's going negative, and he's going toward the left, he's going positive, okay? When n is an odd function, meaning he's x to the third power, x to the fifth power, x to the seventh power, something of that nature, he is going to go opposite directions, okay? When it's an even function, like x squared, x to the fourth, x to the sixth power, he's going to go the same direction. So in this case, they're both positive infinities here. In this case, they're both negative infinities here, okay? So we want to do that for these first three functions. So I'm going to start filling out. As x goes toward infinity, what is the y doing? Oops. Okay, sign. As x goes toward negative infinity. Oh, hold on, I'm not writing. As x goes toward negative infinity, y is going toward blank. Okay, so let's fill those out for all three of these and see what we get. Okay. Oh my goodness, kid. Kiddo. Honey, you need to be good. Here, do you want some? Okay. X goes toward infinity. Y is going towards blank. X goes toward negative infinity. Y is... I'm just filling this out for all three of them so that we can go back and fill the blank in here in just a minute. So when they talk about the leading coefficient test, this just tells us like what the end behavior is doing. Okay, so let's talk about these graphs here. This highest power or the leading coefficient is -1, and it's an x to the third power. So x to the third power does kind of like an S, but he's going downhill, so he's going to do something of this nature. So as he goes toward the right, he's going toward negative infinity. As he goes toward the left, he's going toward positive infinity. Okay, this one is an x to the fourth power, so he looks like a W, and both tails, both the right and the left side, are going toward infinity. This one is an x to the fifth power function, so he does something like this. As he goes to the right, he's going up. As he goes to the left, he's going down, so negative infinity. Okay, so that's what those three kind of look like. Just think about the graph. We don't have to be specific about whether he has, you know, 1 hump, 2 humps, that type of thing. It's just whether he's going up and down on the left and right side. Okay. Then they're going to have us go down here where they talk about zeros of a function. And a zero of a function is just where he crosses the x-axis. So like we're looking for these places here. So maybe your graph is doing one of these. I don't know. And we're looking for those places where he crosses, okay? They will call them zeros, solutions, factors, x-intercepts. So let's see. Sometimes they'll call them roots as well. That's another one. Sometimes they'll call them roots too, okay? So find all real zeros of this function right here. What I want to try to do is break that down if we can. So the first thing that I noticed is that we can take a 2 out of each piece and we can take an x squared out of each piece. And really, since this first term has a negative, let's go ahead and take a negative out of both of them. So I'm going to take a negative 2x squared out of each. And left over would be x squared minus 1, I think. Okay. So after I do that, I have 2 pieces here, and I'm going to set each one of them equal to 0. So negative 2x squared equals 0. And x squared minus 1 equals 0. Okay. If I divide by -2 to start with, x squared will still be equal to 0, because 0 divided by negative 2 is still 0. And if I take the square root, x equals 0. So that's one place where he's crossing. You can see that on the graph over here. And then this guy, what you could do is, if you notice that x squared minus 1 is a difference of squares, you could say x minus 1 and x plus 1. That's what he breaks down to be. So x is equal to 1 and x is equal to negative 1. Or if you just don't do that, you could go ahead and just add the 1 over, so x squared equals 1, and then take the square root. But you have to just remember that the square root of 1, since we put the square root in there, is plus and minus 1. So whichever way you want to think about it, we will end up getting all three zeros, negative 1, 0, and positive 1. And that's going to be the places where he crosses the x-axis, okay? I'm going to skip this box where it talks about those things. Let's go down here where we are drawing all of the information from this function, okay? So apply the leading coefficient test. When they say that, I'm going to plug in and do as x goes to infinity and negative infinity, what's the y coordinate doing? Okay, y goes to blank, y goes to blank, okay? So this is a positive x to the 4th power, so he's going to do a w, something of that nature. And he's going positive both directions. So I'm going to put positive infinity, and number 1 is done. Number 2, find the real zeros. So I'm going to set each one of those equal to 0. 0 equals 3x to the 4th minus 4x cubed. And we are going to try to break him down if we can. So I know that we can pull out, let's see, we can pull out an x cubed, and I think that might be it. If I pull in an x cubed, I'm left with 3x minus 4. And then I can just set both of those pieces equal to 0. So x cubed equals 0, and 3x minus 4 equals 0. Okay, to get rid of the cube on the x cubed, I can take the cubic root, but the cubic root of 0 is still 0, so I have that. Then if I add the 4 and divide by 3, I have x is equal to 4/3. So those are going to be the two places where he crosses. I went ahead and gave you the graph. You won't like on homework problems or anything like that, you won't be given the graph. But I just gave you the graph so that we can see whether we're matching up or not. So 0 and 4/3, that's where he's crossing. And then, so number 2 is done. And then what we say is we plot a few additional points. So where it says test interval right here, we know that 0 and 4/3 are going to be places where he crosses. So what we're going to do is we're going to test the interval from negative infinity until we get to 0, because I want to know what's happening on the left side of 0. And then I want to know what's happening between 0 and 4/3, and then I want to know what's happening between 4/3 and infinity. So this is on the right side of 4/3. So what we do is after we determine our test intervals, we pick an x coordinate. So I know that in this test interval, a really nice number is negative 1. Between 0 and 4/3, a really nice number is 1. And a really nice number between 4/3 and infinity is 1.5 is what they chose. I probably would have chosen them number 2 because I think 2 is probably nicer than 1.5, but whatever. So they take those points and they've plugged each one of these points. The negative 1, they've plugged that into the original equation up here. And they got the number 7. They plugged 1 into the original equation, and they got the number negative 1. They plugged 1.5 in, and they got negative 1.6875. So what that means is, since 7 is a positive number, that means he's above the x-axis here on the left side of that 0. Then he goes negative, which means he's below the x-axis. Okay, then he's positive again, which means he's going up and positive there, okay? Doesn't mean increasing and decreasing, because he's decreasing, but he's still positive. So right here, he's just above the x-axis. Here, he's also above the x-axis, but then here, he's below the x-axis. So that's what positive and negative means. So then we just have some extra points to plug in on our graph, and that's where we get those guys, okay? So let's do that from scratch on this thing. Sketch the graph. So the leading coefficient test, x goes to infinity, y goes to blank, x goes to negative infinity, y goes to blank. Okay, so this is a negative 2x to the 3rd power. Okay, normally x to the 3rd power does that little s, but now he's going down this direction. So he's going negative as he goes to the right, so negative infinity here. And as he goes to the left, he's going toward positive infinity there. So that's my leading coefficient test. Okay, find the real zeros of the polynomial function. All right. So I'm going to erase this, and let's see. Well, what do I want to do here? Find the real zeros of the polynomial function. I don't like this fraction right here. So what I would like to do is let's take the entire function and let's multiply through by -2. How about that? We'll multiply him by a -2. So if I take -2 and multiply him by all three of those pieces, we'll end up with 4x cubed minus 12x squared, and then plus 9x, because 9 over 2 times 2 is just going to be positive 9, okay? And then I can find the zeros from there. I did that so that I could get rid of the fraction in my equation, okay? Find the real zeros. So let's see, what can I pull out? I can pull out an x. So if I pull out an x, I'll be left with 4x squared minus 12x plus 9, okay? And then, oh yuck, let's see. I'm going to set both pieces equal to 0. So I'm going to set x equal to 0, and I'm going to set 4x squared minus 12x plus 9 equal to 0, okay? So I know x equals 0. That's going to be one place where he crosses. But then I have this thing, okay? And that's a complex trinomial. So what I can do is I can take 4 times 9. 4 times 9 is 36. And I want two numbers that I can multiply to get 36, but when I add them, give me -12. So the first thing I think about is -6 and -6. That multiplies to get 36, but when I add them, give me 12, okay? So then I'm going to do 4x squared minus 6x minus another 6x plus 9. I take this guy and I write him as 4 pieces, and then I just group, okay? So I group this guy and I group this guy. So out of this first piece, I'm going to take a 2x out, and I'm left with 2x minus 3. And this one, I'm going to take a -3 out, and I'm going to be left with another 2x minus 3. So my two pieces are 2x minus 3 and 2x minus 3. And if I set each one of those equal to 0, equal to 0, equal to 0, I would add the 3 over and divide by 2. So x would be equal to 3 halves for both pieces. So x equals 3 halves. And 3 halves is this point right here, 1.5, or 3 halves. That's my other place where he crosses. So 2 places, 0 and 3 halves are my 2 places. Okay? And then the last thing that I'm going to do is I'm going to create my test intervals. So if my numbers are 0 and 3 halves, I'm going to look at what's happening on the left side of 0, which is like going from -infinity to 0. Then in between 0 and 3 halves would be 0 to 3 halves. And then from everything on the right side of 3 halves would be from 3 halves to infinity. That's what he looks like, okay? Then we just have to pick some test values. So from -infinity to 0, a really good number is -1. Between 0 and 3 halves, we can use the point +1. And between 3 halves and infinity, we can use the number 2. Again, you can use any number that's in that interval, but I just chose those because those are really nice, okay? So then we're going to take these guys and we're going to plug them. So I'm going to take -1. I'm going to plug him into this equation up here, okay? And I'm going to do this on my computer here. And I got 12.5. So that means he's positive. And that means he's above the x-axis, which we can kind of tell here, okay? If I plug 1 in, I get -0.5, which means he's negative, which means he's below the x-axis between those 2 points. And then if I plug 2 in, I get -1, which means he's below the x-axis again, which is consistent with what my graph says. So some additional points that I have on this graph are the point -1, 12.5. I'm just putting these two columns together. I have the point 1, -0.5, and I have the point 2, -1. And that's going to give me some additional points on my graph, okay? I just picked 3 points that were in the intervals that I was looking at. And I wanted to, the reason why I separate them out into intervals is so that I don't pick 3 points that are all over here on this side. then I have no idea what's happening on this side of my graph. So that's kind of why they have you separated into test intervals, is so you pick 1 point from each one of the test intervals that you're looking at, okay? And that can just give you a better idea of what the graph is going to look like, okay? All right, there we go.